Hello class, in this video I'll be introducing the Fundamental Theorem of Calculus. Let's begin. So in sections 15.1 and 15.2, you learned how to evaluate an indefinite integral. The result was a function whose derivative was the function inside the indefinite integral. For instance, okay, so I have an example here, and notice the expression that I have highlighted in green is called the indefinite integral. The expression that I have highlighted in red is the solution. And we label the solution capital F of x because capital F of x is an antiderivative of lowercase f of x. And we call capital F of x an antiderivative of lowercase f of x because the derivative of capital F of x is equal to lowercase f of x. We will now introduce the definite integral. Which will look something like this. I'm going to box this in purple. And as I'm boxing this in purple, you may see some striking similarities between the definite integral and the indefinite integral. You may also notice something that's not similar. For instance, you may see these two real numbers, one at the bottom and one at the top. Well, what do those two real numbers represent? What are they doing there? What does the solution to a definite integral look like? And how do you find the solution? Enter the Fundamental Theorem of Calculus. It states, let lowercase f be a continuous function on the closed interval a comma b, and let capital F be any antiderivative of f. Then, this beautiful string of expressions separated by equal signs is the Fundamental Theorem of Calculus. And I'm going to explain what this all means in words. So in words, if we can find an antiderivative for the function f of x, then we can evaluate the antiderivative by evaluating the real numbers at the endpoints of the interval and subtracting. Okay. So I'm going to provide an example. It says, what is the value of this definite integral? And what does that value represent? Okay, so if I'm going to find the value of this definite integral, I'm going to apply the Fundamental Theorem of Calculus. So notice, in this case, that lowercase f of x is equal to x squared minus 2x. And we know that capital F of x is equal to x cubed divided by 3 minus x squared plus c. And I got that from the example that I provided earlier. So I can set up the indefinite integral as such. Okay, so now that I have the definite integral set up, notice that all the pieces are present. Okay, so we have our lowercase f of x, which I will highlight in blue. And we have an antiderivative of lowercase f of x, which I will highlight in red. Now all that's left is to evaluate the antiderivative at 3, then at 0, and then subtract the result. So f of 3 is equal to f of 3 minus f of 0. And so I'm going to go ahead and use Decimus to evaluate this. So I'm going to go over here into Decimus. And I already have the function or the antiderivative in Decimus. And notice that I left off the constant. Okay? I'm going to evaluate f of 3. And we get 0. Next, I'm going to evaluate f of 0. Well, we also get 0. So f of 3 is equal to 0 plus c, some constant. f0 is equal to 0 plus the same constant. So this is equal to c minus c, which is equal to 0. So I can write the following. This expression, or this definite integral, is equal to 0. And now that we have a solution, what does the solution mean? Okay, so over here I've drawn a picture of f of x, which is equal to x squared minus 2x. And notice it's a parabola that opens upwards, and it has zeros at x is equal to 0 and x is equal to 2. So I've highlighted the area between the graph and the x-axis in 2 different colors. So if the graph was below the x-axis, I highlighted that area in red, and that is a negative area. If the graph is above the x-axis, I highlighted the area in green, and that is a positive area. So what the solution means is that if we take the area in green and we add it to the area in red, that result will be 0. And that's what the solution to the definite integral represents.